Now we'll start what is a metric space. Since there is a metric space, so what is a metric and what is a metric space? There is a natural question to raise your head. So what is a metric? Metric is a function. Let D is a function from x cross x to R. Then D is called a metric on x if it satisfies the following conditions. The number one is dxy is greater than 0 when x is not equal to y. Second is dxy is equal to 0 if and only if x is equal to y. Third is dxy equal to dyx. Fourth is dxz is less than equal to dxy plus dyz. For all xyz belongs to x. Try to understand. Let D is a function from x cross x to R. In geometrical figures, suppose this set is x cross x. This is R. And D is a function from x cross x to R. Each element of x cross x must be pair xy, x1, y1, x2, y2. Since this is a function, every element must have an image point. So xy equal to dxy, xy, dxy. Since this is a real number that may positive, may negative, may also 0. So D is a function from x cross x to R. Then D is called a metric if it satisfies the following condition. dxy is greater than 0 if x is not equal to y. In languagically, the distance between any two points, x is a point, y is a point, the distance between any two points is always greater than 0. The distance cannot be less than 0, negative between, that is greater than 0. At best is equal to 0 when two points are coincide. Suppose this point is y, the distance is less, distance is less, distance is less. When y is equal to x, the distance between x and y is equal to 0. So dxy is greater than 0 if x is not equal to y, and dxy is equal to 0 if and only if x is equal to y. dxy equal to dyx. That means the distance from x to y is equal to the distance from y to also x, and the distance from x to z is less than equal to distance from x to y plus the distance from y to z. This is called the triangle inequality, x, y, z. dxz is less than equal to dxy plus dyz. So this is called the triangle inequality. If D satisfies the following conditions, then we declare that D is a metric. So what is a metric space? The whole set X with the metric D, this pair is called a metric space. Like in group theory, if G is a non-empty set and star is a binary operation, then G with that operation forms an algebraic structure. That is called a group. Similarly, X is a non-empty set, D is a distance function or metric on X. The pair X and D, that pair is called a metric space. Whenever we say X is a metric space, it is understood that this is X, comma D, this pair is a metric space. Now we write only X for the metric space. Let X is a metric space and S is any subset of X. Let X belongs to X. Small x is an element of X, may here, whatever means that. X belongs to X anywhere. When we say that X is an interior point of S, in figure, S is a set, X is a point. You say that, sir, S is a interior point because there is a round circle. This X is not an interior point. Interior point means these points. But in geometrically it is true, but analytically it is not true. What is an interior point? Let X is a metric space, S is any subset of X. Let S subset X and X belongs to S. X belongs to S. Then X is called an interior point. An interior point of X if there exists a neighborhood nx epsilon such that nx epsilon is a subset of S. That means S is a non-empty set and X belongs to S. Then X is called an interior point of S if that satisfies the condition. Condition is if jadi there must exist a neighborhood of X which is a subset of S. Then we say that X is an interior point of S. For example, suppose S is equal to 1 to the open intervals. This is 1, this point is 2, this is the open interval. Open interval means X belongs to this set, means 1 is less than X is less than 2. X is here. Each point of this interval is an interior point. You take any point, there must exist a neighborhood which is a subset of that set. So this point is an interior point. This point is an interior point. There must exist a neighborhood. Between any two points, there exist infinitely many points. If A is rational, B is rational, then A plus B by 2, that is also rational. A plus B by 2, that is a rational. This is a point, this is a point, this plus this by 2, this is another point. That means this is a non-terminating process. Between 1, 2, each point may rational, may irrational, may natural number, whatever you mean that. That means there must exist a neighborhood which is a subset of that set. So this point is an interior point, this point is an interior point, this point is an interior point. That means every point of 1 to the open interval is an interior point. Suppose S is equal to 1 to the closed intervals. This is the number line. This point is 1, this point is 2. 1 to closed interval means the open interval union these two boundary points. 1 is a boundary point, 2 is a boundary point. In case of open interval, we exclude these points. But in case of the open interval, we exclude this. In case of the closed interval, we include this. That means this point, each point is an interior point. So 1 to the open interval, each point is an interior point. But in case of the closed interval, each point is an interior point. But what about 1? What about 2? 1 is not an interior point of S. S is equal to 1 to the closed interval. 1 is not an interior point. Suppose one may say, sir, 1 is the interior point. Suppose S is into interior points. If 1 is the interior point, by definition of interior point, there must exist a neighborhood which is a subset of that sets. That means 1 plus epsilon may belongs to, but 1 minus epsilon here. that does not belong to the set. So there does not exist any neighborhood which is a subset of that set. So 1 is not an interior point. Similarly, 2 is not an interior point, exact 2. You take any small interval or large interval, it is up to your choice. There does not exist any neighborhood which is a subset of that set. So 2 is not an interior point. But in between, every point is an interior point. What is a open set? Open set. In plus 2 level, we know that what is an open interval, what is a closed interval only. But in higher mathematics, what is a open set? Let X is a metric space and S is any subset of X. Then S is called the open set in X if every point of S is an interior point. If each element of a set is an interior point of that set, then we declare that that set is an open set. 1 to row open interval. Suppose S is equal to 1 to row open interval. This point is 1, this point is 2, 1 to row open interval. Each point is an interior point. There must exist a neighborhood which is a subset of that set. There must exist a neighborhood which is a subset of that set. So each point is an interior point. S is open. A set is called open if every point is an interior. If we set is similarly S is equal to 1 to the closed interval, exact 1, exact 2, this. Each point is an interior point, but 1 is not an interior point, 2 is not an interior point. So S is not open. Every point is an interior point, but 1 is not an interior point, 2 is not an interior point, so that this set is not open. S is equal to 1 to the open interval, so each point is an interior point, so S is open. Then a set is called open if every point is an interior point. This is the definition of an open set. Let S subset X, then S is called open in X if every point is an interior point. Example, S is equal to 1 to open interval. This is open. T is equal to 1 to the closed interval is not open. Is not open. X is a metric space, S is any non-empty subset of X. If each point is an interior point, then you declare that that set is open. Suppose S is equal to set of natural numbers. This is the set of natural numbers. Starts from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the full number. This is the number line. 1, 2, sorry, the 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 2, minus infinity, 2 plus infinity. N is the set of natural numbers. So 1 is an interior point of the set. 2 is an interior point of the set. Though 1 belongs to n, 2 belongs to n, so these points are not the interior points. That means no point of natural number is an interior point. You take any natural number, that is not an interior point of that set. Suppose one may say that's our S, that it belongs to means that must an interior point. Suppose 3. 3 is an interior point or not? If 3 is an interior point, by definition there must exist a neighborhood which is a subset of that set. This neighborhood may contain infinite number of rationals as well as irrationals. Here only the natural numbers. If every element of this set is an element of this set, then we declare that this is a subset of that set. 3 may belong to that. or 3 plus epsilon, 3 minus epsilon, that contains infinitely many points of rationals as well as irrationals. How they belong to the set? So 3 is not an interior point. 7 is not an interior point. Means no natural number is an interior point of natural number set, though that belongs to the set. Similarly, the set of integers, this is I, means I plus union I minus union 0. The number line, this 0, 1, 2, 3, minus 1, minus 2, minus infinity 2, plus infinity. This is the number line. Set of natural numbers, we test it. No point of natural number is an interior point. So what about the integers? I is equal to I plus union I minus union 0. That means set of positive natural numbers, set of negative natural numbers, and 0 including. That set is called the set of integers. Now test each point of integer is an interior point or not. No point of integer is an interior point of the integer sets. 2 is not an interior point, minus 1 is not an interior point, 0 is not an interior point. So that means no point of integers is an interior point of the integer sets, though they are belong to the set. What about rationals? Because we know this is the set of natural numbers, the superset is integers, we test this is not open, this is not open. What about set of rational numbers? Q. Q means the set of rational numbers, Q plus union Q minus union 0, including 0 the set of all rational numbers. And what about the set of rational numbers? Q. Q is equal to Q plus union Q minus union 0. This is the set of rational numbers. Now we test the set of rational numbers is open or not. If it is open, every point must be an interior point. So you take the one point, you test whether that point is an interior or not. Suppose x belongs to Q. X belongs to Q. That means x is rationals. X is rationals. You take any large neighborhood or small neighborhood, it is up to your choice. Each neighborhood contains infinite number of rationals as well as irrationals. Because the set of rational numbers and irrational numbers, they are dense in R. Rational numbers are dense in R. Between any two rational numbers, there must exist a rational number. Between any two rational numbers, there exists also irrational also. So each neighborhood of X contains infinite number of rationals as well as irrationals. If they are the rationals, that belongs to the set. If there are irrational points, how they belong to the set? So that does not exist any neighborhood of a rational number, which is a subset of the rational number set. That means no point of rational number is an interior point of rational number set. Q is not open, N is not open, I is not open, Q is not open. Similarly, set of irrational numbers, that is R minus Q. You take any element, X belongs to a rational number, you take any neighborhood, that may be a small neighborhood or a large neighborhood, it is up to your choice. That does not exist any neighborhood which is a subset of irrational number set. That means no irrational number is an interior point of the irrational number set. So that R minus Q is not open. So what about R? Set of real numbers equal to R plus union R minus union 0. This is the set of real numbers. That is rationals, that is integer, that is natural number. This is not open, not open, not open, irrational, not open, but the real number is open. Means every point of real number you take, X belongs to R. X belongs to R. You take any neighborhood, that neighborhood may contain rational, irrationals. If irrational belongs to the set, irrational that is also belongs to set, because this is the set of real numbers. The set of real numbers means the union of rationals as well as irrationals. That means each point of R, there must exist a neighborhood which is a subset of the real number set. That means each point of real number is an interior point. So that set of real number is open. Let X is a metric space and S is a subset of X. Then prove that the null set phi, if S squeezes, that reduces to null set phi. Phi is a subset of this set. So if S is equal to phi, then this set is open. Phi is open. If S is equal to X, that is also open. That means the null set phi is open, the whole space X is open. This is the theorem number 1. Null set phi is open and whole space X is open. When we prove that S is open, open means each point is an interior point. You take a point interior, then declare that each point of that set is an interior point. By definition, open set, the set is open. Since S is equal to phi, since phi has no elements, how we can take a neighborhood? Since S contains no elements, there is no element in phi which is not an interior point of phi. Negation of negation again possession, not. There is no point in phi which is not an interior point of phi. Not means yes. That means every point of phi is an interior point of phi. Since phi has no element, then there is no element. There is no element in phi which is not an interior point. Interior point of phi. That means every point of phi is an interior point of phi. So which implies phi is open. Suppose we extend the sets that is equal to suppose X. Then what about X? The whole space X is open. Since the whole space is open, you take any element of X, you take that one neighborhood. If that neighborhood belongs to subset of the set, then you declare that each point of X is an interior point. So X is open. Let X belongs to X. X is any arbitrary element, may here, whatever means that. X belongs to X and R is greater than 0. The radius is always a distance. The distance is always greater than 0. The distance between 2 points is equal to 0 when 2 points are coincide. The distance cannot be negative. So R is greater than 0. Then there must exist a neighborhood NXR such that NXR is a subset of X for all X belongs to S and R is greater than 0. That means each point of X is an interior point. You take an element X belongs to X and R is greater than 0, then there must exist a neighborhood of X. Whatever means that radius. May report this is R or this is R, this the radius is greater than 0. Then there must exist a neighborhood which is a subset of that set. That means each point of X is an interior point. Means X is open, the whole space is open, the null set phi is open. This is the first bit of the theorem. I hope you found this video enjoyable. In the next representation, I will discuss about the finite intersection of open set and some theorems. See you next time.